Welcome to Brain Vision.
Alright, let's go ahead and solve this problem. This time we're trying to find the flux of f through s, and f is given as x comma y comma 5. The region S is a little bit complicated. I've already drawn it, but it is bound by x squared plus z squared is equal to 1. That's a cylinder. Y is equal to 0, it's a plane, and x plus y equals to 2 is also a plane, but that one is slanted. And when you combine all of them together, it would look something like this. I would imagine that it looks like one of the bamboo that has been cut diagonally. Okay, now, as usual, we're just going to find the flux for each of the surfaces. One heading down, I1, one on the lateral side, the curvy part, I2, and the diagonal flat portion, I3. Okay, so let's start with I1. As you can see, the normal vector is very straightforward. It's just the plane y equals to 0, and it's heading downwards. So the normal vector is 0, -1, 0. Oh, one thing that I would like to mention right now. Sometimes I like to put the Y on the top. Sometimes I like to put the Z on the top. I rarely put the X's on the top, but I do that occasionally in order to make my drawing look like they're facing upwards, if you understand what I mean. Um, if I put the Z upwards, then this would be a diagonally cut bamboo shape that's facing sideways, and that makes my 3D imagination a little bit tougher, so I really don't like doing that. So that's just one of the things that I like to do. So I would like you to bear with me. Anyhow, let's get back to work. Let's figure out what f dot n is. F dot n would equal to just the middle number, so it's -y. But here we know that y is equal to 0 on the plane y equals to 0. So this is equal to 0, so we don't have to worry too much about this one. The flux of I1 is 0. I2. This one, it's a curve. The normal vector is different depending on the location, so we have to calculate it. This one takes quite a lot of work, so let's go through them step by step. I will start by parameterizing the surface by saying x equals to cosine theta, z equals sine theta, and y is simply y. The reason that why this works very well is because x squared plus z squared is equal to 1. It's a cylinder, and y is just a very straight line, so it makes the cylindrical coordinate system work very nicely. So that's the reason of my choice. So the parameterization with respect to y and theta as our arguments, it'll be the vector cosine theta comma y comma sine theta. Now let's find the partial derivatives. In the y direction, you will get 0, 1, 0. In the theta direction, it will be negative sine theta, 0, cosine theta. The normal would be the cross product, as we've been going through this over and over again. And we will get cosine theta. The middle part, we don't need to worry because you will get a 0 anyways. And the last part is sine theta. Okay. F x is equal to cosine theta, y is y, 5 is 5. So we know that f dot n is equal to cosine squared theta plus 5 sine theta. Now let's move on to the integral. What we're trying to evaluate is this, the integral of cosine squared plus 5 sine theta ds. Now let's worry about the limit of integration a little bit. So let me move this just a little bit over here. There you go. All right. So I would like to make ds, oh, let me erase that actually. I want to do dy d theta. There you go. The limit of integration of theta, first, that one's very simple. We want to have an entire circle, so it's from 0 to 2 pi. Let me erase the s real quick. Now, the y value. This one you want to be a little bit careful. The bottom portion, the circle, y is equal to 0. Now, the top part right here, this is the equation x plus y equals to 2. So we know that from here you can deduce that y is equal to 2 minus x. And let's remember x is equal to cosine theta right now. So 2 minus cosine theta would be the upper limit of this integral. So what you're really trying to evaluate is the integration from 0 to 2 pi of 2 minus cosine theta times cosine squared theta plus 5 sine theta. It's not an extremely difficult integration if you're used to this, but it is still quite complicated. I am not going to go through the details of the calculation, but let me just leave some side notes. Let's recall that whenever you evaluate cosine squared, you can use the identity 1 plus cosine of 2 theta all over 2. And if you want to evaluate cosine cubed, then you can use the fact that cosine squared is 1 minus sine squared. So you can do cosine theta times 1 minus sine theta, sine squared I meant. And then the u substitution of letting sine theta equals to u will actually work out very nicely in this case. So using this identity, you should be able to do the evaluation of the integral without any problems. Anyhow, going through all of that calculation, you will be able to calculate that this is equal to 2 pi. Okay? All right, we're not done yet. We have one more integral to go. Okay, let me put this over here. Now let's move on to I3. Okay, now this one, the normal vector, fortunately, it's quite simple. X plus y equals to 2 is 1, 1, 0. If you need a refresher of why that's going to be the normal vector, you can go to, I think it was chapter either 13 or 15. A couple chapters back, we talked about how to find the normal vector of a plane. So please refer back to that. Okay, and f dot n. This is x plus y. And what do you know? We know that x plus y is equal to 2 on this plane. So it suffices to say that we're trying to evaluate the integral of 2 ds over s, but that's equivalent to saying 2 times the double integral of ds through s, but it's also equivalent to just the area of the projection. And we know that the projection is just a unit circle, so that's area pi, so this is equal to 2 pi. Making the calculation quite simple. So long story short, we know that the I1 has flux 0, I2 has flux 2 pi, I3 is 2 pi, so the total flux is equal to 4 pi. And this is how we do these kind of problems.